this is the notebook. Okay, so I mentioned on Monday the need to, if you're interested in efficiently modeling your data, the need to downsample your data using a method such as Quadrature Decomposition. And what a Quadrature Decomposition does is it looks at the variance of a specified area, a block of pixels of a specified maximum size, and it calculates the variance of the phase within that block of pixels. And if it's above some threshold that you can specify, it will divide that block of pixels up into 4 smaller blocks and repeat the process over and over and over again. And the idea is that eventually you sample your interferogram at a resolution which is dependent on the variance. So areas where there's a lot of variance in the data get sampled more densely, and areas where there's not much variance don't get sampled very densely. And presumably the areas where things are changing are the areas where the information is. And so overall, you end up with a sampling which reflects some of the features in the data. And that's desirable because then you don't spend lots of time modeling things that don't matter. So this notebook that I'm about to go through uses a freely available Python-based sampling tool called Kite, which is part of a suite of tools called Pyrocco, which are mostly seismology, and there's a bit of geodesy in them for studying things like earthquakes. And the Kite tool is excellent. It's in if you want to look at where this notebook is, it's in Prepare InSAR Data in Module 1. And if you haven't got Module 1, you have to run, and France is taking you through what you need to do. Okay, so the first step in this notebook, and I provided the link to Pyrocco if you want to go and see it. My internet server cannot be found. Does that mean I'm dead, or can everyone still hear me?
It worked for me.
Huh.
Pip installs.
Well, okay.
There you go.
Yeah. So I already have them, but what these will do is install those things for you. As I said, that I put a link to what I thought was the Pyrocco webpage, but maybe I can revise that later on. You can certainly find it if you want to Google them. They have a cool suite of tools. And this will install a couple of things. It installs the Pyrocco suite. It installs a non-GDAL UTM to that long converter. I'm probably in trouble for that. But Piyush isn't on the call, so it's okay. Yeah. And Kite, which is separate from the main Pyrocco suite. So having done that, then we can initialize our environment by importing all the packages we need to run this notebook. Hopefully no problems there. And the next cell after that is pulling from a repo I put up there this weekend of a in Turkey. Good to know. So if you click on this, this is pulling it from the cloud very nearby, hopefully, so it shouldn't take very long to download these files to your local directory, and it's pulling the filtered, unwrapped interferogram, line of sight information in a geocoded form, a watermask, and a correlation file. The next thing we want to do is tell our notebook where these files are. And if you'll notice, the path to the files that's provided is the one from my home computer. So clearly that's not where the files will be on your machine. But you can check whether they're actually in the current directory by doing something like this, making a cell, doing a listing, and you'll see that they're actually in the present directory. So you can do PWD, and it tells you where you are, and you can paste that in your cell here. It's always a good practice to know where your files are. So that's why I didn't change it. And you won't have any excuses for not finding the files that you're supposed to be using. Okay, so having done that, it also specifies a few things in this cell about file names. It tells you the interferogram file, the correlation file, the watermask file. Water mask is something that you can make. It's not made automatically, I don't think, by ICE, but it's an ICE command that you can run. I pasted it into the chat some ways up about an hour and a half ago. You can probably find it again, or maybe half an hour ago. But what it is basically is a file of ones and zeros, which is the same size as your interferogram. And if you multiply your interferogram by it, it will mask out water, which is a good thing. Especially helpful if you're looking at islands. A couple more things I've included. I've included wavelengths for the radar, because I want to convert my interferogram phase to displacement. And I've also included a correlation threshold. It's quite a generous one, actually, in this case. But we can mask out points of below correlation from our data as well, because we don't want to include those in our model. So the next few cells are just going to make sure I execute them all. The next few cells are going to, oh, interesting. I need a slash in my path, like so. So everybody do that. Then it will load using the built-in routine in Pyroco. In Kite, it will import your interferogram into a structure. That's the first step. So make sure you have that slash, otherwise it will not be pulling the file. We won't find the file. We can look at the interferogram that we've imported just to make sure that it works, and you should get something like this. You can see there's a discontinuity in the phase in this interferogram, which is the East Anatolian fault, basically in Turkey. And there's, a good 60 radians of line of sight difference across that fault from this earthquake. So, assuming that all works, we move on by importing some other things. And there's some sleight of hand here with flipping the files and things, because the format that Kite uses to load them in has a different reference pixel from the one that we use to load things in. But if you do all these things in the order that are provided, it can account for that difference in reference pixel. And what we're going to do is we're going to use the packages from GDAL to read in the raster data for correlation and also for the water mask, and put them in the same geometry as the Kite package uses. And that should be uncontroversial. And then some people asked in Slack this morning how you could convert your interferograms to displacements. You can do that using commands that are ICE-based. The slash is on the path to the file. If you go up and look at what I did here, I added an extra slash here. You can do that using a Python command that's an ICE script, or you can do it in Python in the notebook. And so here, this line basically takes the layer of this structure that contains the interferogram and multiplies it by the wavelength and divides it by 4 pi. And then you should have converted your interferogram to line of sight displacement. Range change in meters, not in radians. I do some other things here. I mask out pixels with which are not 1 in the water mask. I turn them into nans, and I do the same thing for correlation values, pixels with correlation values that are less than our threshold, and that will also zero those out. And when you plot the resultant thing, you'll see now that you have some things missing from your data. Basically, these are rivers and lakes and incoherent pixels. You can see the incoherent pixels as a smattering of them. The really major features that have gone are the Euphrates River, which is here, which you can see has a rather glorious left lateral offset across the East Anatolian fault, showing that fault is actually active and moving, offsetting the river. And this is a big dammed river up here as well. So this is what we're going to Quadtree, and also you see that the displacements are now in fractions of a meter, whereas before they were large numbers of radians. So all that worked. So the way that the Quadtree package is initialized for Kite is this command here, qt, so the Quadtree dataset equals the scene that we've loaded, .quadtree. And this takes a short while to run, and the next cell after this will be the controls for the Quadtree. And so you can specify the variance threshold, which is this value here, which is basically 0.02 meters squared. But this is something basically that you find by trial and error, and I already did my trial and error, I guess, for this scene. You can specify how many nans are allowed in a block of pixels, and the larger you make this, the more it will divide up pixels around where you have masked things out. So if you make this lower, then kind of it can handle things that are masked out a bit better. But perhaps at again, this is something you can play around with. You might not necessarily want to have no sensitivity to nans, so you can vary that number. You can also specify the size of the tiles, the blocks of pixels that you can get. So you can specify a maximum size, and I've chosen 0.2 degrees, which is about 20 kilometers. It's quite big. And a minimum tile size, which I've chosen 0.01, which is about 1 kilometer, which is reasonably small. So when you run that, it will, oh, interesting. It hasn't done that to me before, but I think it will be fine. Thank you. Why is that not, why is this doing it to me now? I've tested this thing lots of times. All right, so we'll see what we get out. I'm fine forever, people. That's good to know. Maybe I missed a step. I should make sure I just run through all my cells in order. Okay. So it'll tell you how many blocks it divided your thing up into. And did something weird to me. Well, we'll see what was going on in a second. It divided mine up into 117. I think before, when I ran it, it was more like 200. But anyway,
194.
You're getting what?
194.
There you go. That's what you should be getting. So I don't know whether I just missed something because I was talking and not running my cells. Weird.
Yeah, it is strange.
You know, the first engagement with the enemy, apparently, you know, you always turn up things that didn't turn up in testing. Anyway, if you want to see what it did, you can run this little loop, and it'll loop through the what it calls the leaves, which are the Quadtree blocks that it came up with, and you'll get a set of reference locations, which I think are referenced to the reference that it uses for the whole interferogram, which is the lower left corner of the interferogram in lat long. So this is a location that's relative to that, and it will also give you the mean value of the values. And what I'm seeing is that it's not, I haven't done the unit conversion, I think is the problem, because my Quadtree pixel means are very large, where they should be fractions of a meter. What did I miss? I missed this step. Probably. Oh no, I'm going to start from the beginning.
I think that's a good idea.
Because if you keep making my pixels smaller and smaller, amplitude, if I keep dividing by whatever, by lambda over 4 pi. All right.
There you go.
Hey, 194. And now my means for my cells are fractions of a meter, which is what I was expecting. All right, and if you want to plot what that's done to your data, it turns into this. So you can see that almost none of my rivers have made it through the Quadtree because I've basically been very generous with this parameter here, which allows you to basically tolerate a certain number of not a number pixels within each cell. And you'll see also that if you look in the far field away from where we think the fault was, the pixels are quite large in this downsampled data, again 0.2 of a degree. But as you get closer and closer to the area of interest, where area of action, you can see the squares get smaller. So showing that it's sampled finally there. What is the one empty cell? That's probably a pixel that's very close to high variance that has a large number of not a numbers in it. It's probably part of the Euphrates River.
But just to be clear, the NANs are not used. It's just how many NANs are allowable in a cell that will then be rendered as a actual.
Right. You can increase that. You can decrease. If you increase that fraction to like 0.9 or something, then you'll see no blocks at all. And if you make this small, it will. When it finds that a cell has a certain fraction of NANs in it, it will divide it so that you have fewer. It's another condition which is used to divide up your data.
Mm-hmm.
You can play around with that. And if it removes lots of the pixels out here, then you're not really losing much information about your earthquake. So I'm okay with what it's doing, basically.
Yeah, 0.9 basically fills in everything.
Yeah.
Okay.
The last step then, you've completed your Quadtree if you get a picture that looks like this, and if you have, let's say, 200 pixels downsampled, that's pretty good. This is a good number. It's got a good distribution of coarsely sampled things far away and finely sampled things close in, which is what you want. And so once you've played around with this and you've decided that you like the values that you've got, then you can save and export your scene so that you don't have to import it again. And then we can move on to the next notebook, which is where we take that Quadtree output and we convert it to a format that is usable in models. And this was designed actually to be used with a sort of historic code that we have used for a long time to model earthquakes. Those of us that came from the Oxford system, the code written by Tim Wright and Pete Clark years ago called OKIN, which is a command line based thing which reads in text files of a certain format, and basically I have reverse engineered how you make those files with this. And it's a kind of desirable format in several ways because it provides for every pixel, so every one of those cells that we have identified using the Quadtree routine, it will give the location in kilometers in a UTM coordinate system. It gives the value of the mean displacement of that block of cells, and it provides the line of sight vector for that block of cells. If I just skip back to this notebook, one of the files that we downloaded and imported and haven't really talked about are these. Is this file here, los.rdr.geo, and its associated metadata. This file here is basically a two-layer file that contains information on the direction that the satellite was pointing, and also the incidence angle with the ground for every pixel that we have data for. And part of what Kite does, it has the ability to read this in. So at the same time that it's downsampling or loading in the interferogram, it's also loading in geometry information on line of sight, which is pretty pretty neat. And so when we run this notebook here, we'll output the line of sight vector for the pixels that we have identified as being of interest. So hopefully, if you run through this, it will read in the thing you just saved, and it will reapply the Quadtree. I guess I could have just put this in the same notebook and I wouldn't have to redo it, but there's the breaks. Okay, and so now we can use some of the built-in variables of the Quadtree data set. We can look at, for example, what the reference point is, and we can also provide that in both UTM coordinates and in lat long coordinates. So here you go. That's where it is. That's where the reference point of the data set is, which is the lower left corner in Kite. And then we can extract the locations of the pixels from this and output them. So here are just some NumPy commands that extract the things that we're interested in and do some very simple math on them. You can see we're extracting or we're calculating line of sight vectors in components X, Y, and Z from the two angles that are provided in the LOS file. So it's going to do the math and do that for you. And at the end of the day, you'll have for each of those pixels that we have identified in the Quadtree algorithm, we're going to have the line of sight vector that goes along with those. OCIM format requires coordinates to be in kilometers, and so this is just doing a coordinate conversion to kilometers for those pixels, and we can plot the output and see what they look like. And this is what our downsample data set looks like when you plot its coordinates in kilometers with its displacement values in meters. And the last cell will output this to some text files. It'll output the lat long data to one file, and it'll output the same data but with UTM kilometer coordinates into another one. And if we do a listing here, hopefully what you'll see is that there are two new files. The Alazic earthquake, so-called. So we have it's an ascending interferogram. I have a file that's output in lat long .ocim, which is the file type that we give a file like this. And we also have the same thing without the lat long, which is the version that has UTM coordinates in kilometers. So if I did another shell command, we can just look at what's in one of these files. Oh, I have to execute it. So you can see there are basically 7 columns in one of these files. We have an X coordinate, a Y coordinate, a displacement, 3 components of a line of sight vector, X, Y, and Z. So X coordinate is positive, the Y coordinate is positive, and the Z coordinate is negative, which implies that the satellite is pointing east, positive east, and negative up. So it's pointing east and down, which is correct for an ascending track of a satellite. And the last column is just a number, an ID number for that line. So if you get something like this, the columns, I think it says it here actually in words, but it's the X coordinate, the Y coordinate, the displacement, and the 3 components of the line of sight vector in X, Y, and Z, the unit line of sight vector, and some ID number at the end. Yeah, I'm rushing through this a little, but many of the things I have said are there in words too, so you can go back and find them later on.